Okay, so this is the Openrocket kind of mini intro tutorial. So Openrocket is a trajectory analysis software. It's pretty good, but it's mostly just good for subsonic rockets. And most of our rockets are either supersonic or kind of approaching the sound barrier. So the accuracy gets a little dicey. So for our example, I'm just going to use this is a model rocket some old members designed a while ago, like 2 summers ago. It just uses an F size motor, probably like, I don't know, maybe a foot long, the whole thing. Like it's not very big. And so basically the first thing you'll do is you want to build like your actual body. So I'm going to go in, we're going to have to take some measurements. Normally we kind of have these things recorded in a spreadsheet somewhere, so you don't have to actually measure, you can just type it in. So this is the nose cone. The distance here, we'll say it's like 6.37 inches. So that's the nose cone length. So if you click on nose cone, this pop-up comes. So nose cone shape, basically they all follow this shape that is some kind of mathematical equation. So you kind of need to know like who designed the nose cone and like what shape they picked. In this case, it's an ogive nose cone, I believe. But yeah, it's not the kind of thing you can measure. You kind of have to know what somebody designed. And our length, 6.37 inches. Oh, and we also need to check our base diameter. So that's just the diameter of the rocket, which is 3.166 inches. This is a bit of an exercise in using SolidWorks evaluation tools. So you don't need to worry about any of this wall thickness, cardboard. You change the paint to smooth paint and set for all. But basically this wall thickness and this cardboard, like they're trying to get a mass and like a CG for you, but you're just gonna override that. So now that we have our nose cone, there's all these other things too, but they're pretty unnecessary. Let's let close. So just to clarify, the parameters for the nose cone are length, the actual like kind of shape that the profile takes, and the base diameter, which is the rocket diameter. Next thing, we're gonna add a body tube, which is just our fuselage. It's automatically the same diameter, so I just have to measure the length here. I'm not doing a very good job of this, but it will turn out okay. And so our delta Y, 30.25 inches. That's our body tube length, outer diameter, and again, the inner diameter and wall thickness doesn't matter. The paint does because it will determine like kind of surface roughness, which changes the drag and stuff. So we usually paint all our rockets, so smooth paint. So now you can see we have our nose cone, our body tube. Now to add the fins, you have to actually be clicked onto the body tube. So if you rocket up here, click on body tube, and now we can hit fins. So there are all these fin options: trapezoidal, elliptical, freeform. I don't really know what a tube fin is, but we always have trapezoidal fins. They're pretty much standard, I think, for what we do. So the fin parameters are kind of funny. So we have 3 fins, of course, and then you can just leave the cant and the rotation. Chord, if you've never heard the term chord in aerodynamics, it usually means like a length along kind of the airflow. So the root chord is the distance on the base of the fin. The tip chord is the distance on the tip of the fin. The height is like how tall the fin is. And then sweep, you either specify the length, which is from the tip to where it actually reaches the full length, or you can specify what this angle kind of is. So I'll show you all these on the rocket. Kind of took me a while to remember what all these are, but basically, so this would be the root chord, this length, which is 8 inches. Fortunately, this is going to be, let this go. You can just double click. So 8 inches for the root chord. Go back, the tip chord. So that's the tip chord, the length on the tip of the fin, 2 inches. And this would be the height, the distance between these. So we're looking for the normal distance, which is 3 inches. And this is kind of, normally you don't have to measure all these stuff because whoever designs these puts it in a spreadsheet somewhere and just updates it. So you would just have to type them in. You wouldn't have to measure, but it is a good thing, practice. So I'm just going to measure the sweep angle. So if you select 2 lines in SolidWorks, you get an angle 21.8 degrees. So this, the sweep is actually from like vertical, or it's like from the other way. So it's gonna be 90 minus 21.8. Usually it's around 60 degrees. Which, yeah, 68.2 degrees. So there are the fins. You can see if you change the sweep length, like it changes this angle. So you can only choose one of those. And we'll select the smooth paint. So position relative to the parent component is the fuselage. So in this case, the position relative to the bottom of the fuselage is 0, like they're mounted flush to the fuselage, but sometimes you'll have like a small gap. We often just have like a very small offset. So if you have an offset, set that. And then fin cross section is basically like, so if we go into this, it's very hard to rotate without a mouse. If you're watching this later, I don't have a mouse, so don't judge. I just open the fin. It'll be a bit easier. So basically the cross section just means like what shape is like this. So in this case, it's like square all the way up, but oftentimes you have like a taper on the front and the rear, which kind of makes it a hexagonal shape, which there's not an option, unfortunately, because we usually do hexagonal fins, which is another reason why Openrocket is kind of inaccurate. But anyways, square cross section, close. Okay, that's kind of the bulk of your work. You got your rocket built. So next thing I'm going to check the stability. So they'll spit out, it's very small, but they do give you the CG and the CP. Oh, actually, sorry, pause. You got to measure the center of gravity because that's their, so to measure the center of gravity, it's measured in inches from the tip of the nose cone. So I made this plane that's just like on the very tip of the nose cone. And here you can add the center of mass just in like the assembly reference geometry. So if you select those 2 things, evaluate, measure, the distance is 20.8 inches. So to change the mass and the CG, you got to double click on sustainer, click override mass and override center of gravity. Oh, sorry. I also realized, so various trajectory analysis softwares like measure things differently. In Openrocket, they measure the mass and the CG without the motor. So you actually have to go in, suppress the motor, rebuild, and then measure your center of mass. So 18 inches is the actual, because they're gonna basically when you select the motor, they recalculate it for you, which is honestly kind of annoying. So I'll put the center of gravity at 18 inches, and we also have to measure the mass. So mass is under mass properties, 495 grams without the motor. So 495. And so we also have to put our motor in so they can recalculate the center of gravity here. Before I do that, is there any questions? Are we all good so far?
So far, I'm okay with it.
Okay, awesome. It's kind of a lot to take in, but there's obviously this video will be up, and then there's lots of stuff on the wiki too. So to add a motor, you have to click on motors and configuration at the top, just this next tab, and hit body tube. So this will mount a motor in the fuselage, which is what we want, and hit new configuration. And so now on the body tube right here, you double click. So it has this automatic list of motors, which is really nice. This is already filtered by Cesaroni because that's the one that we use, but that motor in this example is an Estes. Sometimes you have to like look up motor information. Like it's not something you usually know off the top of your head. In this case, it's an F class motor. So I'm just gonna narrow our selection to F. Basically, impulse is like the kind of, it's a performance metric of the rocket, like how much impulse it can deliver. So O being the most and A being like, you know, like a little battery sized motor. So for context, like N motor would take you supersonic. Our current rocket has an M, but it's just barely reaches Mach. Kind of depends on your mass and stuff. So F you can legally launch and buy, from like a hobby store. So in this case, it's an F-15. So select that, press OK. So now we see it tells us our stability is 1.45 calibers, which means the center of gravity is 1.45 rocket diameters above the center of pressure. So that's pretty good. Technically, competition, you need to have 1.5 calibers off the rail. So in this case, like something we might do is you need to add mass. So we might say put some mass here on the recovery bulkhead. I don't want to go through all that because it's a little tedious, but basically if your rocket's really unstable, you got to do some math to figure out how much mass you need to put to get your CG to where you want it. Basically, like you have your CG solve for mass rather than usually you calculate CG. But 1.45 is definitely enough for a model rocket. So now that everything's all good, we can go into flight simulations. It's already started one up for us for this motor. And we can go run simulations, and that's pretty much it. So it gives us velocity off the rod, apogee, which is our max height. I'm not really sure what optimum delay means, but max velocity, max acceleration, time to apogee gives you all these things. You can go in and edit your simulation. So you can change your wind speeds. We don't really have a good like metric of what wind speeds we should be using. That could be something, a project for someone to look into if they're interested. Yeah, we could just kind of wing it with the wind data, honestly. So you can set your launch site. I don't really know like coordinates where I am right now, so we'll just leave that. But the launch site does matter in terms of like elevation, will affect like pressures and stuff. So will affect like your height. So when you're doing more precise simulations, you should make sure you get the location and its altitude above ground. The launch rail, so that's a 17, or what is it? What's 204 divided by 12? I think that's the competition launch rail that just got saved in there. Okay, that's 1 point. It's a bit more than 1.5. 204 divided by 12. Okay, 17 feet. Yeah, that's what I thought. So that's the competition launch rail. You're not going to use a 17-foot launch rod for this, little rocket like this. I'll just say for interest's sake, it's 6 inches long. Yeah, and if you're doing a simulation for like a competition rocket, this information is always available. The angle, you usually launch at like a small angle of attack, usually like 1 or 2 degrees. So I'll leave that at 1 degree. And then it's red because we've changed stuff so we can run simulation and stuff changes a little bit. So you can plot and export this now. So yeah, you can get altitude, vertical velocity, can plot stability versus time. So red is the stability margin, blue is the CP location, and green is the CG. So as you can imagine, like the motor is going to burn fuel. So the CG is going to like move up because you're losing mass at the rear of the rocket. And since like fluids kind of behave differently at like different speeds, the center of pressure changes because like your average location of drag will slightly vary with speed. So that's why the center of pressure changes. But we can see that it's like pretty, I don't know why it's so low when it says, interesting. But you can also, yeah, drag coefficients versus Mach number. That's kind of cool. So there's different types of drag. Friction drag is from friction. Base drag is like drag on the rear of the rocket, and then pressure drag, all kinds of stuff. And you can also export data. So if you want to like all this stuff, you can just like export. You can get all this data and export to a CSV and then like kind of sort it and graph it and stuff. And then I guess I'll show you one more thing that's kind of cool is you can have like multiple motors and run them all. So if you're trying to size like what motor you want, let's say, yeah, we don't know. We know it's probably about an F size, but we don't know like between which ones. So let's select this one. Okay, so this one is more stable, 1.58, still good. And then if we go to flight simulations, we can run all these simulations again. And so you can compare different motors, which is cool. Yeah, I think that's all I have for, oh, I forgot one thing. This rocket does not have a boat tail, but oftentimes, or our rockets usually do. So it's just kind of a conical thing like that on the end. I'll just say this is like 1 inch for the sake of So usually for the boat tails, we'll specify the length and then the aft diameter, which is this diameter. Let's just say it's 2 inches. And smooth paint. We can see if that how that affects the trajectory, I guess. So 571 and 1270. So it made this one a little higher and this one a little lower, which is kind of interesting, but it just goes to show like how boat tails can kind of help you adjust your trajectory if you need. So do you guys have any questions?
So basically, when you're looking at the plot and like when you're looking at the graph and everything, how what is the ideal situations, like the ideal graph? How should it look like?
That's a good question. So it kind of depends what you want. In general, you want to like minimize your drag and maximize your apogee. If we're doing a competition rocket, we want our apogee to be really close to like the category we're in. So either 10,000 or 30,000 feet. And then in general, you want to watch that your max acceleration does not go too high because otherwise your components will not be able to survive, like your electronics. And you want to watch your stability kind of your stability margin, you don't want it to be too high. Like if it gets around like 7 or 8 or 6, it's kind of concerning because it can actually get so stable that it will blow straight into the wind like a weather vane and then just like kind of you lose a lot of apogee.
So basically, in a sense, stability isn't really, it's not like the more stable it is, like, like the general idea is like what we think is stability is a good thing, but apparently in this situation, stability may not be a good thing.
Yeah, there's kind of an acceptable range. You need to be a certain amount of stable, but if you get to be too stable, yeah, you run into issues. Sometimes it's really hard to avoid because you'll need to put so much mass to get like your minimum allowable CG, and then the rocket burns off so much that it just like the CG just moves like way up to the front and it's hard to control your center of pressure. So things can happen, but yeah, it's ideal to keep it below like 6. And then, yeah, as for the actual shape of the plots, like I would not know what the ideal shape is. They kind of, we usually put them in our reports and stuff, but they're kind of hard to just like analyze just looking at them. It's more like I kind of look at the extreme values of, apogee, velocity, acceleration, stability, and that kind of is a better clue. Yeah, I will stop the recording.